Hey kids, time to do surface integrals. All right, so we've been doing the last video, we did a double integral, right, with surface area. And we talked about how we could, some 3D surface, right, if we had a function z, some 3D surface, we could kind of use the cross product of the vectors to, along the surface, to find the area of the parallelograms and then sum them all up, right? We showed you how to kind of go from parametric to a regular function f, so that we had that square root of the partial squared plus 1 squared, right? So now we're going to go to a surface integral. And what I mean by that is taking our surface area formula, right? Again, double integral over a surface. Here's my partial squared plus my 1, technically also squared, over an area. And I might have a surface here or here where this formula, right, some function describes it, I can calculate the surface area. Well, what if now, which is a little bit harder to picture, I have a surface integral. So I want to integrate over a 3D surface, and that 3D surface, G, a capital G, I'm going to call that function, over the surface area. It's a little bit harder to picture, but maybe some things that you might think of over here, maybe this is some kind of, I don't know, artist, creation here of some kind of mold or model, and there's varying density. So this object is maybe thicker at the bottom than it is at the rim, and there's some function G that describes that varying density. Or G is electrical charges across some field. This is some field and there's electrical charges all on it. And G describes those electrical charges, and I want to sum them all up. Or if I have this sphere, right, maybe this is even the Earth, and this green cloud here is my function G that is maybe the temperature, right? The temperature at a certain level of the Earth, all around the Earth, and it varies, right? So it's kind of a 4D picture almost, if you will. But what if I wanted to, for instance, find the average value of the surface of the temperature of that, right? I could integrate over the interval, right, over the surface area of a sphere. So kind of cool, right? So we need to take this expression, the surface integral expression, and transform it. And we're going to transform it. Notice that this piece all came from, remember we were doing the cross product of the differentials, and we showed how, right, along the surface, we showed how that could be rewritten using the cross product here, so that we could just have our explicitly defined function z and use it. Well, now I'm going to insert. Notice that I've got the exact same situation here, and all I'm doing is inserting an integrand. Here's my integrand. I have some surface, some 3D surface, x, y, and z is expressed by taking domain values from x and y, and that's how I get my surface. Pretty cool. All right, so let's just do some examples here. So example 1, I want to